Hi everyone. Today I'm going to show you how to do some matrix transformations on objects polynomials. To start with, let's begin by popping a few points onto the plane. Now to keep this simple, I'll just put 3 points here and then I'll come down to find my polygon tool and I will connect A to B to C to D to get a polygon. Notice how it's labeled the edges as well. Now I don't particularly want the labels on the line segments. They're going to clutter up my diagram a bit, but I will keep the labels on the points. I might also click on the polygon itself and show the value of the polygon. The area of that polygon is 1. Now go to Algebra View. We can start to see the things that are here. They're my points, there's my polygon, and those are the line segments. Now don't hide the segments. That tends to make it look a bit weird. So I want to see the segments. I just don't want the labels. Now I'm going to do a transformation, but the first thing I want to do is I don't want to have individual vectors to each of the points A, B, and C. I want to have a matrix capturing all of that information. So I'll call this matrix P for polygon, and I'll use curly brackets. A matrix is a list of elements. There's 2 rows. So the first row is going to be the x coordinates. So the x coordinate of A, a comma, and then the x coordinate of point B. Finally, the x coordinate of point C. Then a comma outside. So you can see here I've got a list of 3 data values. Then I'm going to make another list. That'll end up being the second row of the matrix, and this will be the y coordinates. Again in order. It's important to have the same order. Y coordinate of B, and then y coordinate of C. If I hit the enter key, it formats it like a matrix and it shows me the nice formatting. So this first column is literally point A at position 1, 1. Point B is at position 3, 1. There it is, and so on. Now let's find a transformation matrix that we could use. Will I use a rotation? Okay, let's do a rotation. I need to have an angle theta. So go to Greek letters, put theta equals, don't worry about what the picture's trying to do at the moment. I'm going to use the slider command. The value will be starting at 0 going to 360 in steps of 5 degrees. So that's just changing a variable. Now I need my transformation matrix. Now this will probably be the first of many transformations I want to do, so I'll call it T1. Again, it's a matrix, so curly brackets. Now the first row of the matrix is a list, and I need the cosine of angle theta, comma, then I need negative sine of the angle theta. Go beyond that curly bracket, put a comma to separate the first row from the second row, and then I need the sine of angle theta. Don't forget commas between elements in a list, and then the cosine of angle theta. Let's try that. Now I've got theta set at 60 degrees. I happen to know, and you should too, that the cosine of 60 is 0.5. That doesn't look like it's working. Now the reason is because GeoGebra is reading this to mean cosine of 60 radians, not degrees. We can fix that easily enough. If you go to the function tab here on the keyboard, there's a little degree symbol. If I click into here, just behind where the theta is, and put a degree symbol, that's it's actually a command for GeoGebra to convert the number 60 in from degrees into radians and then work out the answer appropriately. So I'll just put the last one in there as well. And this time, everything's nice. The cosine of 60 degrees is 0.5. The sine of 60 degrees is root 3 over 2, which is about 0.87. So that's nice. We're almost home. Now I need to actually perform my matrix multiplication between matrix T1 and matrix P for my polygon. So I'll call this P1. That's polygon, the image of polygon P. And it's the transformation T1 multiplied by, that's the asterisk key, multiplied by polygon P. These are the coordinates. Now nothing appeared on the screen because this is in the computer memory. I will need to extract the coordinates here for point A1, point B1, and point C1 being the images of A, B, and C. So I'll show you what I mean. I'll create a point which I call A1 and put brackets. Now, how do I get hold of that number there, which is part of a matrix? Well, it belongs to matrix P1 and it's in row 1, column 1. Put a comma to separate. Now the y coordinate is also part of P1, but the y coordinate is here, row 2, column 1. And there's my point A1. I like to have a different shape. There we go. Now let's just check to see what's happening. Does it look like point A1 is the image of point A under a rotation about the origin? If I rotate by 180 degrees, there I am. That looks like an imaginary line. Now I didn't draw the vectors this time like I did last time, but it's still operating in the same way. Now I'll go ahead and I'll find image of point B and C, and then I'll make a polygon. I'll just pause while I do that so the video is not too long. Okay, so here we are. I have found the value of point B1 and C1, the image of B and C, using the same method. And then I made a new polygon connecting point A1, B1, and C1, made it all look beautiful. And as you can see, rotating, I get the image of my first polygon over here. I've also shown that the area is the same. That's interesting. Now, that's using an alternative method. Instead of having vectors pointing to every point, transforming each of the vectors individually, we've put all of the points together into a matrix, which I labeled P to represent polygon. There's my transformation matrix. P1 is the image of polygon P under this transformation. And then I had to extract the coordinates of points A1, B1, and C1 from this result matrix. And then I drew a polygon. And I did the same thing where I took the labels off the edges. So we could, of course, go ahead and use polygon number 1 as the input to another different transformation. I could do another transformation further down here called T2. Maybe not a rotation, maybe something else. And then P1 could be the input and give an output P2. So P transforms to P1, then P1 transforms under a different rule to P2, and so on as many times as you like. And I think that's enough for this lesson. Thanks for watching.